Thank you, and I'd like to thank Jean-Christophe and the organizers for inviting me and for arranging a wonderful conference. Lots of interesting talks. And yes, this department combines everything from sort of soup to nuts. This work was primarily supported through a part of the U.S. National Science Foundation called Coupled Natural Human Populations, and I was on a couple of others of these, and where you had to get people from multiple different campuses and different departments, et cetera. But in our campus, in this one department, there was me, there was a field biologist, there was a bioeconomist, a political scientist, and all of us are just down the hall, which made the organization of this much, much easier. So I want to start with an outline, which is what I'm going to do is introduce a particular invasive species. So what I'm actually going to do is going to be a little less comprehensive than the title would suggest, but the points, I think, are going to be very general, and I could have added some other systems I'm going to work on. So then I'm going to start off by basically developing a model, going through a series of steps, and simplifying it, and then try and figure out what the best management strategy is. And it was very nice to hear that discussion this morning of invasive species, because the problem I'm going to discuss is primarily invasive species. And then we're going to look at a very interesting complication, and I'm assuming, we'll sort of see how it goes, I'll have some more time to look at a more general approach. And to some extent, I should say, I'll welcome questions and requests for clarification during the talk, partly because I'm going to introduce some ideas that may be a little bit new in terms of other disciplines here, already hinted at by the. So another way of looking at what I'm going to do, and I'll try and return to these later, is basically sort of think about how you might use the kinds of approaches we have here to guide management, and sort of emphasize why mathematics is a particularly powerful tool, and introduce some issues related to bioeconomics, which a lot of ecologists typically have not paid enough attention to, in particular with invasive species. And then throughout, we're eventually going to emphasize some things which really raise some mathematical challenges, which in this case we can deal with very simply because of the nature of the problem, but in other cases would be much more of a challenge. And one of the ways, sort of, just even before getting started, is that theory is absolutely vital, is that anytime you're doing management, you're making a prediction. If I do this, something will happen, or if I don't do this, something will happen. And in order to make a prediction, you need a theory, and theories, when it comes to ecology, are often best expressed in mathematical terms. So we're going to see a couple of pictures of the study organism, or maybe study the invasive species, and it's not going to be quite the same invasive species. It's essentially the same, but not quite, in two different locations. This is one picture, and what does it look like to you? If you blue. But what is the? All right, let's go to what does that look like right there, or that dot right there above my pointer? That dot. That dot. If you had a scale that was much smaller than this, actually it would look like bacteria on a Petri plate. No? Okay. But this is actually a 1 kilometer, on the order of 1 kilometer square. And this is a mud flat in Willapa Bay, which is just north of the mouth of the Columbia River. I certainly wouldn't expect you to know where Willapa Bay is. I assume you know roughly where the Columbia River is. No? Border between Oregon and Washington? It's got probably more water than may even have more water than the Mississippi. It's because it comes out of a very wet area. And this is the same location 2 years later, and this thing spreads like wildfire. It spreads from the clones to form meadows. And what's very handy is that here it's invading bare mudflat so that you don't need anything sophisticated to see what's going on. And so this is another way of looking at the data that I just presented pictorially in a graph, which shows that over this period, you had a change from native vegetation is completely absent, essentially. It's mudflat is the native vegetation, and it goes from mudflat replaced by this plant, which is of the genus Spartina. There must be Spartina on French coastline, because there is on the English coastline. So I just don't know for sure. And in Willapa Bay in particular, it had a negative impact. There's an oyster industry there, which actually consists of introduced oysters, but they're farmed. And also, it's one of the very few places where birds can stop off to feed on the west coast of the US, because the west coast is very different from the east coast. Another view of the organism is here, and you see these clones, and they're spreading. That's all vegetative growth from a single plant forms one of these round objects. And those we'll call clones, which we'll abbreviate by C, and then when they grow together, as maybe you might see in this part of the picture, we're going to call that a meadow. And although I won't emphasize it so much today, another reason that we're very interested about this plant is because it's what's known as an ecosystem engineer. It accretes sediment, and there's certainly a lot of sediment here to accrete. And it then raises the area where it is above the surrounding area, and that's going to become more important a little bit later. And actually, when you want to go look at this stuff, you get to ride around in the airboat and deal with all sorts of crazy insurance issues with our university. So we've heard also, what's nice is that going later in the week, lots of terms have been introduced. We heard this morning about an Allee effect. We will distinguish here between a strong Allee effect and a weak Allee effect. The strong Allee effect would be negative growth at low densities, and a weak Allee effect would just be higher growth at higher densities, the higher per capita growth. And basically, start off with a very simple simulation. And if we want to do management, simulations aren't that much good because it's very hard to do essentially optimization based on results from a simulation, and very hard to understand what's going on. And so what we'll do is we'll simplify the model. First, I want to point out that, in fact, there is an Allee effect here. And what you see is in the green are the clones. They're by themselves, and the blue is in the meadows. And what happens is that this is a plant which is wind-pollinated. And therefore, if it's one of these clones and they're self-incompatible, a clone cannot be fertilized by pollen from that clone. And so you have to have different things close together, and then it produces more seeds, which is what you see on this graph, that the blue, many more seeds per square meter of occupied area. And this is an interesting case. It's where the wind blows in exactly the same direction every day of the year. Not like here. It's like if you've ever landed in San Francisco on a plane, you've always landed in exactly the same direction because the wind blows in the same direction every day of the year. And it's obviously quite easy to put together a spatially explicit simulation model. And we did this. Everything that I'm going to go through here is carefully parameterized from field data. And one can run this on a yearly step, which is very handy. These things reproduce once a year. There's some vegetative stuff. Things can be broken off in storms and move around. That can be moved around, but primarily the way it occupies new habitat is seeds, which then also get dispersed in the water. These things are living in the intertidal. It's a salt marsh intertidal organism. The pictures you saw before where I showed the actual intertidal. Willapa Bay is sort of at high tide, it's all covered. At low tide, 70% of what was underwater is now above water, and it lives right sort of in between. And we can do this, and the Allee effect does what you expect. It slows the invasion, And what that says is, in fact, yes, we want to include the Allee effect in this. And at this point, I should start to mention some of these collaborators by name. You saw Don Strong's name earlier. He's a faculty colleague. Fritzi Grefstad worked up in Washington. Jenny Seville was a grad student with Don. Heather Davis was a grad student with Don, and Cass Taylor, whose first part of whose name is cut off, was a grad student working with me, all on this first part of this project. As I said, we don't want to have a full model like that. We'd like to try and get a very simple model that's analytic, and in order to get something analytic that we're going to be able to deal with, we're going to deal with implicit space as an approach, and we've heard about that this week too. And the part that's a little hard to read says that parameters are dependent on the density and numbers of individuals. So there's some nonlinearities that are covered up by the way I'm going to display this. So the first thing is, where do seedlings come from? New individual stalks. They come from clones. And here, the way we measure things, you might say, how do we count? We measure them both in terms of what we do with the field measurements, and the we here usually means they. I didn't go in the field that much. Did get to ride on the airboat, though. The measure things in terms of the area occupied, which is something you hear about the first time you take demography in an elementary ecology class, but you very rarely see people doing. Usually they count. Well, here area is the only sensible way. So there's a fecundity of clones and a fecundity from meadows. That's where the seedlings come from. Then where do the clones come from? Well, the clones basically come from seedlings that turn into clones the next year. And they also come from clones growing, and we call them clones basically more or less until they grow together to form a meadow. And the clones grow at a rate GC. And a fraction eta of the clones we think of as turning into meadows, and a fraction 1 minus eta remain clones. And then finally, where do meadows increase in area? Two ways. One is that clones turn into meadows, and the other term there is meadows in getting more area. You may ask about one thing, where's mortality? There is no mortality here. They really do not get killed by anything in this area of the world, which is actually too bad. And this species is Spartina alterniflora, which is one that is native to the Gulf Coast and East Coast of the United States, but not native to the West Coast. And if we compare, we can parameterize both models. The solid line is the simulation model. The dashed line is our analytic model. And so we can use the analytic model as a tool for doing optimization. And so there was a very large effort to control Spartina in this Willapa Bay, partly because the leader of in the Washington State Senate, so the Senate for the state of Washington, not for the US, but the leader for the Washington State Senate, this area was in his district. So they got money to control the Spartina. And you're running, in this case, equipment and salt water. It's expensive, it's tricky. There is some chemical spraying going on. That's a little tricky in water. You don't want to do it. And you do things like try and destroy it. It's actually, in Willapa Bay, it really is gone. So you might ask questions like, how much Spartina do you need to remove every year, for example, to get rid of it within 10 years? And you have another potential problem, is that there's another bay just north of Willapa Bay. And when people first realized this Spartina was a problem, and actually it was there in Willapa Bay for a long time, nobody did anything because there was a single clone, and it had to take an accident that by chance, even though it's self-incompatible, that just by chance it got to reproduce. And once there were two, then it took off like wildfire. So one of the problems with invasive species is you don't know they're a problem until they are a problem. And not too far away from here is the place where calaper got introduced into the Mediterranean. And again, people looked at it, oh, this is cute, it can't possibly survive there. And by the time they realized it was a problem, it was too late. And so that's another issue, is getting rid of it there. And then the other sort of classic thing, and it goes back to a paper well known, and the answer is this is not even really the right question, but sort of, do you go at the edge of an invasion, or do you go for the interior where it's producing the most seeds? And again, that sort of ties into the talk we heard this morning about spatial spread and pushed and pulled waves to some extent. So what's the control strategy? It's quite simple. We're going to do it as though, in this case, we're only going after clones and meadows, and just to simplify things. And we have a certain budget, and to simplify, we're going to talk about it as a budget in terms of area. You can make this more complicated. T sub t in any given year, and you can spend a fraction x of that budget on removing meadows, or a fraction 1 minus x on removing clones. So the clones dynamics are given there. You've got the innate dynamics and the control. And the same with the meadows, where again you get to choose the fraction of that you remove. And this is a nonlinear problem that turned out that, in some sense, the most efficient numerical method, and this is work with Cas Taylor, that came out in, I think the reference is coming on the next slide, was to use genetic algorithms to do this. And basically, one of the questions would be, if you want to get rid of it within 10 years, and there's the reference, you have to figure out how much the initial invasion you have to remove. And so the solid curve that's dark that you can see is how much of the area is initially invaded, and the bottom is a measure of the age of the invasion, how long it took to get there, and then you can see how much you have to remove. And the answer that you come up with as to the optimum is right here, which is that if you have a very low budget, you essentially spend the entire budget on clones the first few years. And then once you sort of have gotten rid of all the clones, and you'll notice that over here, it looks like, oh, we've switched from clones to meadows and then back to clones. Well, that's because in this year there really were no clones, because the clones came from the meadows, and so you've gotten rid of them all, et cetera. So basically, you go after all of one type to begin with, and then when there's no more of that type, then you go after the other type. And that's kind of interesting. It came out of this optimization approach, but we don't really know why. And here, if you have a low budget and you do the optimum, and you have a high budget, you do the optimum, you see that you can get rid of it. If you actually do the wrong thing, and you have a low budget, and you do the meadows first rather than the clones first, you fail. And so, to summarize this, basically, you have, and the thing in the bottom right, the risk part is the part I didn't go through the details, but we add in the importance of trying to reduce the probability of invading the next habitat. So this could handle small problems, but there's a way to handle larger problems, which is to turn this into a linear programming problem, which can handle problems of arbitrary size, essentially. And we'll see how that works. And again, it's very, very simple. The idea behind it is that early in the stage of invasion, and you can say, well, gee, I'm going to claim it's linear. How can I get Allee dynamics? Well, you can sort of fake them, because the Allee dynamics are weak. So the clones basically reproduce less than the meadows. So once you put in the age structure, you can, in some sense, get the Allee dynamics. And in the early stages of an invasion, you can ignore the density dependence. And it's this simplification that makes the issues that arise, which have to do, in some sense, and we'll see them more a little bit later when we make the problem more complicated, are easier to deal with, because if it's linear, you can deal with things over sort of arbitrary timescales. Nonlinear problems, we've seen a lot this week on asymptotic behavior, but nonlinear problems on intermediate timescales are much more difficult, especially if you add stochasticity. So basically, early invasion, which is when you probably can control it, you can ignore the nonlinearity, and if you look, right, so we write down the equivalent of essentially a Leslie matrix. In this case, it's a stage structure matrix. And then obviously you can write down a complete solution. You hope your undergraduate students can do that. Where M is a matrix which tells you sort of the change in area of clones and if you include seedlings, the 3 types as a function of the areas the year before. And this is, as I said, naturally a discrete time situation. So management would say that you remove something, and there's sort of, we've gone back and forth over the years as to how we index things, because neither way seems quite right. But so here what we do is we add in the idea that we remove this vector h of sub t is the amount of the different stages that we remove in a given year, and what you then end up with is the amount you would have had without the management minus the amount you removed. And what's handy is because it's linear, then you see in the equation on the bottom that the amount after t years is the amount you would have had without management minus the amount you had in the first year that you removed and what that would have turned into after t years, minus the amount that you removed in the second year projected forward to what that would have turned into after t years, etc. So because of the linearity, it all comes out neatly. Yes, the removal part is important, right, for your bank account, yes. Well, you could do this with fisheries if they were all linear, but they're not. And I just want to point out that what I did before was a strategy, and again, this is sort of like the discussion we heard about effort control versus a threshold control versus other ways of managing fisheries, that we could as well put our management strategy in as something that's multiplied by the vector representing the population. Or, and then once again, if we've, once we've done that, we can still project that forwards. So we have a system where everything is nice and linear. And you could combine all these strategies and still have something that's easy to deal with. And we can apply this to the same sort of question. And very simply, here we've got a graph illustrating what would happen as we increase the annual budget along the along this axis. Annual budget's going up. Along this axis is time, and this is the population size. And what you see is with the optimal strategy, you have to, the more you spend, the earlier you are, the better off you are. It sort of makes sense. If you've got something, get rid of it early. And this is trying to get rid of things in 10 years with a constraint. And something else interesting happens. But in this case, we can understand why. If you look at the optimal strategy, the fraction of each stage, in this case green for isolates, red for meadows, that's removed by control, and isolates is just another name for clones, in each year under the optimal strategy. And what do you notice here? Once again, you go after one type. Well, how many people here know the basic fact about linear programming? The solution is always at a vertex, which says that this is no longer as a surprise, whereas with the genetic algorithm, yes, you could sort of convince yourself, but once you've done you sort of see the power of mathematical approaches, and they're really often particularly useful in some sense in data-poor situations. I mean, if you really have a completely detailed model, in some sense, the mathematical tools, you can just go to the computer and if you really know all the parameters, you really know everything, you can project forwards. It's when you only know things vaguely that actually the mathematical tools maybe are most valuable, because then they give you a better way to understand things. And this is, did I manage to repeat this twice? Yes. So, acting as fast as possible is the key, and the rewards come, in some sense, right away. And sort of one kind of sort of, I think, general idea, and it turns out what's interesting is that times I've talked about this in combination with work that I've done thinking about coral algal grazer systems, and the first couple of steps were the same. You start off with a simulation model that's spatially explicit. Biologists like those. You can understand what's going on. Very hard to understand and do essentially management approaches. Think about that. Switch, do an analytic model that's spatially implicit. Show that you get similar behavior. You trust the analytic model where you can do optimal management. And then we switch to an even simpler analytical model. And in some sense, I would argue, but this is, I mean, I'm not demonstrating this, but I'd argue that often what you want to, you're better off doing more or less exact solutions of quite simple models rather than doing very approximate solutions of complex models, though they both have their place. Okay, that looked good. Now what happens if the situation gets a little bit more complicated? So we're going to move from Willapa Bay to San Francisco Bay, and I assume most people know where San Francisco Bay is. And there, the invasion is a little different, and there's a problem here. There's a balance. We've got, and they have multiple objectives. So some of you may even recognize, if you're good, the sort of skyline of San Francisco in the background. And that's Katie Zaranga. And she's standing in the field, and the short, polite, calm, mellow stuff is the California native, Spartina foliosa. And it also inhabits or grows in the intertidal between high and low tide on mudflats. But it does not grow as high nor as low in the intertidal, and is not as prevalent an ecosystem engineer. And then the stuff that she's standing right next to is the invasive, which is actually a hybrid between Spartina alterniflora and the local Spartina foliosa. At times I may slip and refer to that as alterniflora, but it's the hybrid. And that is an invasive that has a number of negative impacts, again, because it grows higher and lower in the intertidal. So it sort of destroys, in some sense, coastline access, et cetera, and fills in flood control channels. And we would be in the same situation as before, except for this organism, which is a bird, and I'll also flip names between here because I'm going to refer to it by its common name, but the birding people managed to change the common name, so it was the California clapper rail, it's now the Wilson's rail. I think that's right, I always forget. And if it could talk, it might say that. It's actually on the US endangered species list, and as I tried to point out that the hybrid alterniflora outcompeted the native, and the bird was very happily would use the hybrid, the invasive species, as habitat instead of the native. And so you can't just remove everything as fast as possible, which is what you'd like to do. And there is, again, an ongoing project of removal. And part of the reasons for these dots on the, so your left, is what the map looked like in 2005, and the most recent data had when I did this. This is a hybrid, alterniflora bifoliosa. The map on the right is 2011, and it's different locations. The size of the dot is how much, and it's in acres, not hectares, how much invasive Spartina there was at that location. And this is another complication that I'll return to briefly at the end, I think, is you say, well, why do we do it by so many dots? Well, this is partly reflects the fact that there's at least, in the sort of courses description, there's something like 27 different management areas that are responsible for coastline along there. So one of the times when we did not get the money the first time. There was some stupid reviewer who said, gee, on part of it where we're talking about this, why didn't you use cooperative game theory to describe the interactions between different government agencies instead of non-cooperative game theory? And that showed that person had never dealt with government agencies before. But there is an overall coordination. And so let's look at the dynamics here, because before you would have said, gee, very simple, get rid of the invasive as fast as possible. There are real costs to the invasive, and I'll emphasize some of that in a little bit. And so both the native and the invasive, we need to think about their stage structure. We need to separate out, in some sense, clones and meadows. And the bird, and you see there is a, whoops. Where'd it go? The bird, as you see, is hiding here or here, but not here or here, because the bird only uses meadows as habitat. And so what we can do is we can think about which levers we get to pull. And this is another sort of general feature when thinking about the biology that's going to be important and, again, makes things more complicated. So one of the things we can do is we can go in, and we meaning the people actually doing this, and you can remove meadows of the invasive species. You can go in and remove isolates of the invasive species, the clones. In either case, you're turning things into bare ground, the thing in the middle. You can remove, no, you can't remove, but you can restore, you can plant isolates, you can plant the native, but that arrow points to a place where there's no, the big blue arrow points to a place where there's no black arrow. You can't plant meadows. If I could insult an engineer, I might say very simple, just plant meadows, but you can't do that. The biological constraint is often there. And so biological dynamics are often slow. If you do something with fish and you're asking them to recover, it may take a long time, go on and on. And that is an important point. So I want to develop the model. We'll see what the results would look like, and we can do it in the same context that we've already done with something that in the end is really linear. And it gives us and we'll touch on robustness, et cetera, because you might say, gee, it looked like it was heavily invaded. So we have a vector of area of isolates and meadows of the invasive. So H stands for hybrid, for invasive. The I superscript stands for isolates, and the M superscript stands for meadows. We just restrict to two classes. And maybe you could think of that as a column vector if it's, as it really is. And then we do the same for the, whoops, how did I do that? Oh, we have a similar vector that I'm not going to write down that would replace the H's by the F's for the native, which we'll use F for foliosa. So H is the invasive, H for hybrid, I for isolate, M for meadow.
X for horrible, F for fire.
That could. And then we have a vector that represents one part of our management strategy, which is eradication. I for isolates, M for meadows, E for eradication. And then we have another vector which represents restoration, but that vector always has a 0 in the second position because we can't plant meadows of the native. And once again, we can use a spatially implicit model. We have a vector of the area of the isolates and meadows. We've got the eradication, we've got the restoration, and then we've got the innate dynamics here. And then once again, we've got the terms representing, so we're letting E and R both be positive, the way we're representing. E and R represent the two management tools that we apply each year. And the objective is to remove and minimize the cost. So we have some time cap t that we want to end up with nothing, so that h, the vector representing the hybrid, or the horrible one, is that what you called it? The horrible one should be 0 at time t plus 1. And here I'd like to mention something that's really important that, to an ecological audience at least, you might have to emphasize. There have been papers that said, oh, gee, it's so horrible. The cost of invasive species in the US every year is X. And they do that by counting up how much people spend to get rid of the invasive species. Well, that's not really the cost, because if the invasive species was causing no damages, you probably don't want to spend to get rid of it. Now, how you actually calculate the damages, that's very hard as to what you say. And this is in terms of all sorts of things. And so ecologists are doing much more connecting to bioeconomics. And in this paper with Becky, Apanch, and Neil, basically, we looked at control, just general principles for control of the spread of invasive species. We were not worrying about establishment. We were not worrying about that aspect or the arrival, but just merely the spread. And the sort of one of the major points here was pointing out the importance of actually worrying about costs and benefits. And so that'll come up later. And so if we do this, we want to minimize the costs. We have costs over t years. And so we sum over the years. One of the costs is, so this is a cost of the actual, the cost of actually spending to eradicate the invasive isolates. So it's a unit cost times how much you remove. This is a cost, a unit cost of removal of the meadows. We have a unit cost of planting of new isolate natives. And then, very importantly, we have to have a cost of damages, because otherwise, the cheapest thing to do, clearly, would be to do nothing. Subject to many constraints. And that term at the end, if we're going to be a little better with our economics, we're also going to put in the discount rate, the idea that and some things in the future are not worth as much today as they are today. And there's a discount rate. And we have a bunch of constraints, and I didn't emphasize this so much before, but constraints which then continue this linear aspect. The first constraint is the budget constraint, saying that you have a limited budget in any given year. Those are all the sort of costs that you're putting in, so this is whatever budget you have. And I should go back and say that this is the total, essentially the total value of what you essentially total expenditures, both in terms of actual direct expenditures and the cost of damages over all the t years. And the bottom one says, this is the idea, well, yes, we have multiple objectives, but you kind of, the only way you can deal with multiple objectives, the two objectives are, number one, maintaining habitat for the endangered species, and number two, getting rid of the invasive species. And so the second constraint is saying that you have to have enough meadows of either the H or F in order to keep everything legitimate. We can worry about reinvasion, and this sort of says, again, something about discount rate and the idea that just like, let me go back here, just like the converse of the fishery, if the fish grows at a very slow rate, that the economically optimal thing to do might be to liquidate the fishery, take your money and go do something else. That's why redwood forests might be cut down, because they grow very slowly. And then the might be there is not just a might. And again, linear programming. And there is the group I mentioned on the first slide, the invasive Spartina project, gets a contract. They manage it basically and coordinate everything. I may say a word or two about that later. So we get information from them with some struggle. Estimate both costs of removal and damages. Damages include things like loss of property value. I had somebody say, well, gee, you're just worrying about rich people when you're doing this, because these are the ones that are right by the shore. flood control, removal costs, the actual, we can estimate from actual costs, and then we have something in some sense, I guess that maybe it should be minimized or with a minus sign. It shows you that this problem, again, is just a big linear control problem which can be solved arbitrarily quickly. And once again, the first thing is that what's there now is what would have been there without the control minus the projecting forward the control. And the second term, which I won't explain, is simply the converse. What you have of the native is what you would have had there without the restoration, plus the contribution of the restoration. Again, linearity makes everything simple. We can express the costs and write them all down so that in some sense they all end up being linear terms, so everything ends up being linear in terms of the things we can actually choose to do, namely the controls and the restoration terms. Another constraint you might not have seen is that obviously you can't remove what's not there, so that in some sense you could almost think you might drive something negative because of the benefit, but you can't do that. That's still a linear constraint. And this whole thing makes lots of assumptions. So, for example, it's linear, so we at least tested by doing what a standard economist would do, which is write down a standard control problem that's familiar to many of you, if not all of you, even if you're not an economist, but this is their sort of bread and butter, this kind of optimal control problem. And NPV stands for net present value, which is really what we're computing, the total value of the thing. And the economists made us do this. Jim Sankirko was the economist. And you get the same answer. And I may have time, maybe not, to say that you make a number of assumptions, you can stochastic stuff, you get the same kind of answer. And you get a picture that looks like this. And let me go through. This, on the top graph, is the state of the system. The bottom graph is, or the bottom panel, is what you actually do. So you start off with a time where you go after the isolates, the things in orange essentially, of the invasive species. And again, you spend as much as you can on those. Again, you're at a vertex. Then you go through a time where you get rid of the meadows of the invasive species. So IS stands for invasive Spartina, NS stands for native Spartina. And at that point, it's mainly invasive meadows. And there's very little of the native meadows around. So then you go through a stage where you start replanting the native isolates so that they can start to take over and replace the invasive meadows once they turn into meadows. And you then go through a stage where you slowly remove the invasive meadows so that the sum of the invasive meadows plus the native meadows is always above that threshold shown by the dashed line in the top panel, which is the state of the system. And the difference is that if you look at the bottom picture, one big thing is that the optimal investment, in the beginning you spend as much as you possibly can, and then after that you dribble out your budget, which is a very different heuristic than just getting rid of an invasive species, where you should spend as much as you can, as fast as you can. Here, economically, you're much better off over the long term to slowly spend at the end. And this is what I've just said. Use the entire budget at the beginning, replant native Spartina after you have a place that pays to do this, and then you slowly remain while the Spartina grow into meadows. Use a small fraction. And basically, timescales show up differently for different problems. So things like invasive species, something which is sort of negative, where you don't have to wait for a biological timescale to act, go as fast as possible, you may need to take into account the biological timescale. And when you put biology together with politics, which is basically what the bottom paper is, I won't talk at all about, you run into some interesting mismatches, because the human timescales are the ones you may be able to fool around with. The biological timescales, you don't have very much. And you can think about sort of converses of this problem. There are times where it may be you have to act faster, and the human timescale can't act as fast as the biological timescale. You could think of things like Zika, Ebola, etc., white nose syndrome in bats, things like that. So at this point, I've got some tentative conclusions, which are that we have a general method for dealing with this. The key result is grow slowly and not use the entire budget. And if we've got nonlinearities, of course, which are going to be really important, things would get more complex. And I've tried to do this in a simple setting, show things up. I'm not really going to have time to do this second part, which is to really put in nonlinearities. And this is work with Adam Lampert, a former postdoc. And so I'll just maybe give a few highlights of this. Go on. Is we approached a general aspect of restoration. And again, you do this because of the potential economic benefit to restore what we might think of as ecosystem services, provide habitat, prevent storms, preserve water, aesthetic stuff. And problem is that restoration is expensive. And are there general principles that come about with restoration? So what stage of things to restore? The bottom is restoring, say, essentially maybe artificial coral reef, artificial oyster reefs. And you have a goal in your initial state. And again, it only makes sense to do this in terms of something economic. So you have costs and benefits. And as I said, I don't think we've heard that much of the economics here. And I will set up, we have a per capita growth rate, we have noise, and we have the human intervention at the end. So we have the innate dynamics, stochasticity, and our possible management action. And the objective is to find the optimal, through time, the optimal active restoration strategy. And again, we do this present economic value, so we integrate over all future times of a benefit, and there's an implicit dependence on time. The benefit, which is a function of the population size, we think of N as being good, a desirable species, or desirable. And we have a cost, which is increasing and convex. You try and do more active restoration, and restoration is in here is displayed in units of the species. And we have a biological restoration threshold, so we assume there's an Allee effect. And once you get past the Allee effect, then after a while, if the, oops, yeah, I can do it here. If you're above this level here, and you go away, the thing should slowly grow, because I've got this blue is the growth curve versus the population, and that's the 0 line. If we go above here, it should grow, but it turns out the benefit to cost ratio says that you want to restore early and you want to restore late. So you want to do some active restoration here, because if you wait, it's going to grow so slowly that you're going to more of a benefit to do some active restoration for a while. And this displays the, in ways that take me a little bit longer, you get this, the threshold itself depends only on C1, only on, if you're an economist, this would not surprise you, it depends on the slope. The actual strategy as to how much you should restore depends on the entire cost function. But again, you've gotten this sort of simple heuristic, or simpler heuristic at least, that when you should be spending to restore is much easier to calculate. We can do analytic solutions for linear growth, for quadratic growth, and discounting, as I suggested earlier, may result in a decision not to restore. And we can then do this and make this, the problem stochastic. We can compute the net present value, where P now is a probability density that follows the Fokker-Planck equation with a specified initial condition. And it's easier to sort of display what's going on if we ignore temporarily the role of discounting. And demographic noise and environmental noise can change cases where you would restore to cases where you wouldn't restore. And in this sense, your decision as to whether or not to restore may depend on the entire cost function. So stochasticity sort of, and again, this sort of fits in with the theme in a slightly different way, where earlier this week we heard someone talking about how if something was stochastic, you actually, in some sense, it uncovers more of the dynamics. Therefore, you sort of see more of it. Well, here, if it's stochastic, even the threshold depends on all the dynamics and not just on all the entire cost function, and not just that simple ratio. And so, more generally, they applied the systems with multiple variables and multiple restoration pathways, and we're actually working out some of the details of this a little bit more carefully. You go through a stage where you don't do any active restoration. You don't then, go through a stage in the bottom left, here. If you're sort of too far away, you just give up. There's a place where the system would recover, but it pays economically to give it a hand. There's a time where it's growing quickly, where it doesn't pay. And then once again, when it gets close to a goal, it's going to approach the goal slowly, right? Once it's approaching an equilibrium, if this, say, is an equilibrium, you know that it moves slowly, so it again may pay to do things actively. And so that could be useful. And so just as conclusions for this part, which I know I went through quickly, there's some very general principles. Restoration is becoming more important. There's some general principles. We can express this in terms of marginal growth rates, which would make an economist feel very warm and fuzzy. Discount is obviously plays the same suppressive role that it typically would. And I want to finish up with just 2 more slides. One is I want to go back to the goals, which I mentioned at the beginning, and sort of see how I've done. And the first goal, for using theory, I would argue that there's a great value to simple models, because with data-poor situations, you can't really parameterize complex models. And those are the times where we probably need the most guidance. Otherwise, we really wouldn't need the help. And that shows up in the second, where again, the math plays a big role because we can get heuristic results. The bioeconomic issues become important, and they're really challenging. I sort of glossed over the cost bit in estimating it, but that's really true. And this idea of the role of the timescale set by biology, and the fact that what you really want to have to be able to do is stochastic systems, but not either over a very short term and not asymptotic, raises all sorts of interesting mathematical challenges. I mean, I think it's in some sense related to some of the issues that came up in Odo's talk about dealing with epidemics and everything we hear with epidemics. And some of the things that are going in the future and very recent stuff, actually during this week I heard 2 papers got accepted, which is a good reason to be here. One is a part of a colloquium that I was in, so it's a sort of an overview paper on timescales, which sort of goes over some of the things, but just sort of reviews them and emphasizes some other issues, so nothing really particularly new. Some of these political aspects are kind of interesting. Mark Lubell is a political scientist in our department, and looking at the role of sort of networks in driving how people actually get the information out to control the Spartina in this complex network. Now we want to connect it to the biological network as well as the information network. And with Adam, we've got a bunch of things we're finishing off. He's since moved to Arizona State as an assistant professor, but we've still got some things to finish. So thanks for your attention. I'd be happy to answer any questions. And you, and then Mark, you had your hand up, right?
I'm exhausted.
Yeah, and then more.
Yeah, so in this, okay, well I guess we can turn to the slide. So I was going to ask about the optimal strategy for controlling when we have the birds.
Yes.
And the kind of threshold of the meadow.
Yeah, the optimal strategy, what about it?
Yeah. So when you have this optimal strategy, one thing I noticed is that the kind of gradient between switching between the two different actions of removing these meadows and replanting the isolates, they're quite sharp. So one thing I was wondering is what would the effects of this be if you somehow kind of mistimed this switch or misestimated the threshold? Would there be an excessive kind of risk of overshooting?
So there's a little bit of, I mean, I covered up a couple of things here. One of them is that this threshold that's not determined by us, that's determined by the US Fish and Wildlife Service. But just in general, here's a case where at least for the Spartina, you really do know exactly how much is out there. That's very easy to estimate. Population dynamics of the birds, of course, is a bit harder. But presumably you would want to take a cautious approach, and one could investigate, we haven't done that here, but you certainly can investigate the change in the overall cost of moving that threshold up and down, which would then tell you sort of, as you're putting in a precaution to save more habitat, how that would happen. And this, this aspect where even this particular trade-off, where an invasive species is habitat for an endangered species, there are some other examples in Australia, tamarack in the US, etc. But that's a good point. One would want to, we put this as the best strategy. Nobody asked, unless Mark, well, I'll let Mark and got a question.
Yeah, so like there were lots and lots of ideas that were very interesting, and one that I had some kind of intuitive reaction to, it didn't quite feel right, was this one that it was with the Spartina, where you spend a lot right off the bat, and then you eke out the remaining amount over a long period of time.
Yes.
And so my question is, if the environment in which you're operating is highly variable or stochastic, would that change your strategy?
My guess is if it's highly, then you have to figure out what your objective is. So do you want to, so the question is, well, I guess everybody heard. So do you want to optimize the expected return? Do you want to minimize the risk of a bad return? And typically, if you were to try and sort of ask humans what they would do, it's something in between just minimizing total risk, because then, of course, you know what to do there, and between doing the idea of maximizing the expected return. And so that we do find that in some sense the results are robust to small levels of stochasticity. Another issue would be if there's very large levels of stochasticity, and then that makes things much harder.
Thank you.
Okay, so I think thank you very much.